In this video, we're going to find the intersection points of polar equations. And solving these are going to use some elements from solving trig equations. And we're going to use graphing capabilities to check for intersection at the pole or origin. You're going to see this technique of finding the intersection of polar graphs in Calculus 2 when you're finding the area between two curves in polar form. So example 3, find all exact points of intersection for each pair of equations. So we have r equals 2 sine theta and r equals 2 minus 2 sine theta. So first let's get an idea of what these look like. So here in red I have 2 sine theta and in blue I have 2 minus 2 sine theta. Well, we can zoom in. And notice that they do intersect at the pole or the origin, and then there's two other angles at which they intersect, two other points as well. And we're going to find these algebraically, but it's probably not that difficult to find where they intersect here in Desmos by visual inspection. So they do intersect at the pole. So we have 2 sine theta equals 2 minus 2 sine theta. So we're just looking at, again, where the graphs intersect we're going to set the left and right hand sides equal to each other. So we have, r equals 2 sine theta and r equals 2 minus 2 sine theta. This we can substitute in for this. So adding 2 sine theta to both sides, we get 4 sine theta as a half, and divide both sides by 4, we get sine of theta as a half. And that's going to give theta is pi over 6 or 5 pi over 6, which, again, we can see if we change this to radians. Ooh, that was kind of weird. We have pi over 6 for one intersection point and 5 pi over 6 for the other. Now, to get the value of r, just plug each of these into either equation, and you'll get r equals 1, which, again, this is this first one's the unit circle here, has a radius of 1, so this is the 0.1 pi over 6. This is the 0.15 pi over 6. And don't forget they also intersect at the pole, or the origin. So they intersect at the pole, and then 1 and pi over 6, and 1 and 5 pi over 6. All right, part B, we have r equals 2 and r equals 3 cosine theta. So let's take a look at the graph of part B. So in green, we have r equals 2. And in purple, we have r equals 3 cosine theta. Well, first thing to note is they do not intersect at the pole. So they only have two intersection points, one being right here and the other being right here. And notice they're in between exact values here, so we're probably going to have to use some approximations at first or use some inverse trig functions to label it. So we'll set them equal to each other and solve. Divide both sides by 3, we get cosine theta equals 2/3. And again, this is why we don't have an exact value, because if we look down our cosine column, there's no 2/3 there. So theta is the inverse cosine, or arc cosine, of 2/3. So that's about 48.2. So if we look at this one, this is our inverse cosine of 2/3. That's about 48.2 degrees. If we take that 48.2 away from 360, we'll get what the total number of degrees rotated here is going to be. So it's about 311.8 degrees for this point down here. Now we are going to change these back into radians, and again, this first point here, this 48.2, was the arc cosine of 2/3. So we can express this first point as 2, and then the arc cosine of 2/3. For this second point, we got 311.8 by subtracting the 48.2 from 360. So its exact value in radians would be 2 pi minus the 48.2 degrees was arc cosine 2/3. So our second point has the polar coordinates 2, and then 2 pi minus arc cosine 2 pi over 3. So we would have gone 2 pi radians, but we had to backtrack that 48.2 degrees, or we had to backtrack that inverse cosine of 2/3. All right, example 3, part C, we have r equals 3 and r equals 6 cosine 2 theta. So let's take a look at those graphs. Should have a circle and a rose. Whoa, gotta zoom out here. Okay. So here we have in green r equals 3, and in orange we have r equals 6 cosine 2 theta. First of all, they do not intersect at the pole, so we don't have to worry about that. But we do have a total of 1, 2, 3, 4, 5, 6, 7, 8 intersection points. So let's set them equal to each other. We get 6 cosine 2 theta equals 3. Divide both sides by 6. We get cosine of 2 theta is a half. And solving this trig equation, cosine is a half at 60 degrees and 300 degrees. So we have 2 theta equals 60 degrees plus 360n. Remember the cosine period is 360 degrees. We also have 2 theta equals 300 degrees plus 360n. So dividing both sides of both equations by 2, we get theta equals 30 degrees plus 180n, and theta equals 150 degrees plus 180n. So in terms of between 0 and 360, we get 30 degrees and 210 degrees for theta, and then we also get 150 degrees and 330 degrees. So we have the points 3, 30 degrees, 3, 150 degrees, 3, 210 degrees, and 3, 330 degrees, which we could convert those to radians as pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. But there is an issue. And if we look at how many intersection points we've listed, we've only listed 4, but clearly from the graph there's 8 intersection points. So what's wrong? Where are the other half of the intersection points? Where are the remaining 4? And the idea of why we haven't gotten those yet is because going back to polar equations, r equals 3 is a circle where the center's at the pole and the radius is 3, but also we get the exact same graph if we do -3. So we actually have 2 equations to solve. We had the one we started with, 6 cosine 2 theta equals 3, but we also have 6 cosine 2 theta equals -3. So solving that one, we get cosine 2 theta equals -1/2, which gives us the 120 and 240. Dividing by 2, we get 60 plus 180n and 120 plus 180n. So here are the remaining 4 angles, the 60, the 120, the 240, and the 300. So we have -3 for r, 60, -3, 120, -3, 240, -3, 300. So converting those to their radian equivalents, we have 1, 2, 3, 4, 5, 6, 7, 8 solutions, which matches the 8 intersection points of those 2 graphs. So got to watch out for that sneaky r equals 3 being the same graph as r equals -3. All right, that about does it for this video. Thanks for watching.